Hello students. In this last segment of this course is elementary thermodynamics for all. I am going to discuss how you deal with real systems. So, today's topic is thermodynamics of real systems, and I am going to show you how to generalize some of the principles that we have developed in this course so far to describe any system whatsoever. So, for this purpose, let me go back to the first law of thermodynamics. So, for an infinitesimal process, I know that the change in internal energy is dU, and dU depends on dQ, which is the infinitesimal amount of heat exchanged between the system and the surrounding, and dW, which is the infinitesimal work done on the system or by the system in the during the process that we are studying now. And let me remind you that these del cut, these symbols, they represent the fact that dQ and dW are inexact differentials, whereas dU, the differential change in the internal energy U, it corresponds to an exact differential because U is a state function. Now, we have already seen that especially in the case of ideal gases, I can assume the work done to be entirely pressure volume work. Under that condition, dW can be written as negative of P external into dV. Okay. We have seen extensive application of this, and we have also seen that for a reversible change of state, by the design of the process at every stage of the reversible change, we can equate the external pressure to the pressure or the internal pressure of the gas. If I put this expression back over here, then dW becomes minus P dV, where P is the internal pressure of the gas, and then if I take that expression and put it back in the first law of thermodynamics, I get dU is equal to dQ minus P dV. Now, this is going to be the starting point for us to extend the application of the laws of thermodynamics to any general system. So, let us start by saying that if I want to apply the same concept to other types of reversible work, in general we will assume two things. We will assume that dW is given by x dx. So, obviously, I understand that depending on the kind of work you are doing, you will define x and you will also define small x. So, what is the capital X? The capital X by definition is an intensive variable representing a generalized force. I know that work is force into displacement. Here I have not specified the nature of work. So, I will say that here I am representing dW in a generic form. Therefore, capital X is representing a generalized force, and I would assume that from my experience of different types of reversible work, X, that capital X, is generally an intensive variable. The next question that comes is, what is small x? Small x turns out to be an extensive variable which is representing a generalized displacement. If I compare this relationship to the relationship that I have written over here, what is capital X in the case of pressure volume work? Capital X in the pressure volume work is minus P. What is small x in the case of pressure volume work, that is the volume of the system that I talk about. Therefore, the generalized force is coupled to the generalized displacement. In the case of pressure volume work, it is minus P dV, and we will see what type of form capital X and small x can take up if I take a very generic set of examples of other types of reversible work. So, let us take some of these examples. The first example, of course, is applicable to fluids, where you have a pressure volume work where dW is given by minus P dV. Now, I have chosen 3 different examples over here which are very far from the fluid. The first example is an elastic rod. Let us consider a thin elastic rod. It may be a metal wire, it may be a rubber tube, a thin rubber tube, and I am going to apply a tension F on it, which would result in a change of the length of the rod. So, if F represents the tension, then this is going to represent the analog of pressure in my example for the fluids, and therefore, I am going to use the tension F as my generalized force capital X. Now, here I see that the generalized displacement is the length L, and accordingly I find that dW is equal to F dL. If I go to the example of a liquid film, you know that you can create a soap film on a soap solution by pulling a set of square shaped wire over it. You try to pull that soap solution, you will produce a liquid film. Then in that experiment, I find that the generalized force is the surface tension gamma. Now, surface tension gamma is the force that holds the surface together, and it will resist any change in the surface tension. And here the quantity that I am trying to use as the displacement is the area A. And therefore, I know that the infinitesimal work done while changing the area of the liquid film from A to A plus dA will be given by gamma dA. If you think of a little more complicated example, you have magnetic solids. And in the case of a magnetic solid, the generalized force that you would use is the magnetic field B. And the magnetic field B will produce a change in the magnetic dipole moment of the sample, which I represent by the vector m. Now, unlike the previous 3 examples, now I have 2 vectorial quantities representing my generalized force and generalized displacement. Therefore, when I calculate the scalar quantity, the infinitesimal amount of work done, I would write down a scalar product, that is a dot product between the 2 vectors B and the infinitesimal change in the vector dm. So, as you see, then irrespective of the nature of the system, I can always write down the term dW, and therefore, I can go back and work out the entire thermodynamics starting from the first law of thermodynamics. To keep things simple, I have chosen to work with this specific example of an elastic rod, which may be a metal wire or which may be a rubber rod of length L at a finite temperature, and let us see how we can make useful application of thermodynamics to the study of the properties of an elastic rod. Okay. So, as I have mentioned here, the system that I have chosen is a thin rod made up of metal or rubber, and this is of length L as shown in this figure, and this is being maintained at a temperature T. Okay. Now, what I do is I do an experiment where I place the rod under an infinitesimal tension dF, and therefore, I would see that I will hold this end fixed and I will apply the tension on this end. And the outcome of the experiment is that the length of the rod changes to L plus dL. So, what is the infinitesimal change in the length of the rod? This is this amount as shown here, that is dL. Now, if I want to write down the fundamental thermodynamic equation for this system, obviously, I will write down du is equal to TdS plus FdL. So, I am using a combination of the first and the second law of thermodynamics. Therefore, if I am carrying out this infinitesimal stretching of the rod reversibly, I can replace dq term by TdS, and I have replaced the dW term as FdL. As you know that there are alternative forms of the thermodynamic equation, and I will be focusing on the change in Helmholtz free energy, because that is the thermodynamic potential when I am maintaining my system at a constant temperature. So, let us work it out. So, what is Helmholtz free energy? By definition, Helmholtz free energy is equal to U minus Ts. Therefore, I can write down dF is equal to du minus TdS minus SdT. That is trivial. Now, what I am going to do is, for my given system, I am going to replace this du from here in this equation using the fundamental thermodynamic equation that I have written down by the combination of the first and second law of thermodynamics. Therefore, I understand that dF turns out to be TdS plus FdL, and then I am left with the other two terms as before. And now I can simplify this equation by cancelling out the terms plus TdS and minus TdS, and this gives me the other fundamental thermodynamic equation, that dF is equal to minus SdT plus FdL. And since I am using a system at a constant temperature, therefore, I would use this equation for understanding further application of thermodynamic principles to this system. Okay. So, what is the consequence of writing down dF equal to minus SdT plus FdL? I know that dF is an exact differential, that is because F, that is the Helmholtz free energy of the system, is a state function. Therefore, I can immediately write down that minus S from this particular expression, that must be related to the partial derivative of F with respect to T, keeping L constant. At the same time, following the same logic, I can write down F, that must be equal to partial derivative of F with respect to L, keeping the temperature constant. So, now you understand that I have used the properties of the first order partial derivative of F to write down these two equations. I also know that the second order derivative of F with respect to L and T should be the same irrespective of the order in which I have taken the partial derivative. Now, using this property, I can now write down this particular expression by writing out the first order partial derivatives explicitly. So, here on the left hand side I have del f del t L. Now, what is del f del t L? If I go back and compare it with this result, I understand that the part highlighted in blue here is nothing but minus S. Similarly, if I just go and look at what this term highlighted in purple means, this is nothing but F. So, what can I write now? I am going to replace this part by minus S, and I am going to replace this term by F, and this is the equation that I get. I get del S del L at constant temperature is equal to minus del F del T L. Now, that immediately tells you that the exercise that I have been carrying out over here, it is essentially the derivation of Maxwell's relation, and therefore, for this particular system, this is an analog of the Maxwell's equation that we know for the pressure volume work. We will next go ahead and try to understand some further implication of having an analog of Maxwell's equation like this. And the question that we pose here is as follows: Is it possible to estimate the change in entropy of a wire as shown here, of an elastic rod as shown here, in terms of any of its measurable properties? Now, as you see here, del S del L T, that you are looking at the change of entropy of the elastic rod as a function of the amount by which the rod is stretched under isothermal condition, and I am trying to estimate this particular quantity. So, in order to do that, using the Maxwell's relation, I need to find out del F del T L. Now, obviously, I need to relate this quantity to some measurable property of the elastic rod. Now, the understanding of the properties of elastic rod is well documented in the literature of physics. So, the next task that we are taking up is this: how do we estimate the change in entropy of an elastic rod in terms of any of its measurable properties? So, let us identify some of the response functions of the chosen system. In an elastic rod, what you find is the most important response function is what is known as isothermal Young's modulus, and this is represented by this notation E t. Now, by definition, if by applying a tension, if I produce some stress, then this stress in this case is given by dF, that is the infinitesimal tension, divided by A, that is the infinitesimal tension per unit area of the rod. Here I have assumed that A, the area of the rod, remains more or less unaffected by the at a given temperature, and this produces the strain epsilon, which in this case is defined as dL by L. So, the fractional change in the length of the rod, which in this case is an infinitesimal quantity. By definition, then I will have E t, that is the isothermal Young's modulus, that is equal to stress divided by strain. Now, if I just use these two expressions over here, then I can write down the isothermal Young's modulus as L by A into del F del L T. if you would remember that this is exactly the partial derivative that has been related to the change in entropy in our previous slide. Therefore, to estimate the change in entropy, the first response function that I identify here is the isothermal Young's modulus. Now, if I look for another response function which will turn out to be useful here, I find that the second response function that I am going to use here is linear expansivity at constant tension. So, this is alpha f. So, alpha f by definition is the fractional change in length of the rod with respect to temperature at constant tension. So, once I have these two response functions defined as given here, I am going to use a cyclic rule. Now, the cyclic rule basically here would be written in terms of f, t and L. So, I understand that del f del T L should be multiplied by del T del L f into del L del f T, that must be equal to -1. If that is so, then I can very quickly write down that del f del T L must be equal to this term, which is inverse of this term, multiplied by this term, which is inverse of this particular term, and I have absorbed the -1. Now, I am going to identify these partial derivatives with the response functions of the system. For this purpose, I have kept the negative sign outside and I have divided the first partial derivative by L and multiplied the second partial derivative with L by A. Therefore, to maintain the balance, I have to multiply this entire right hand side by another area A. So, now I identify that this term is nothing but alpha f and this term is nothing but E t. Therefore, I can very easily show that del f del T L, this partial derivative, this is expressed in terms of the area of the rod, the isothermal Young's modulus E t, that is a characteristic measurable property of the material of the rod, and alpha f, which is a linear expansivity at constant tension. Once again, that is another property that can be measured in the laboratory. So, what have we learned from this exercise? From this exercise, we found that there is an analog of Maxwell's equation, which tells me that I can find out the change in entropy with respect to the change in the length of the elastic rod under isothermal condition. And I then find that the partial derivative of del f del T L, which determines this change in entropy, is related to some measurable thermodynamic properties of the elastic rod. Therefore, I can find out del S del L T to be equal to A, which is the area of the elastic rod, then E t, which is the isothermal Young's modulus, and this is the linear expansivity of the rod under constant tension. Now, this also tells me something else. If I have a metallic wire, if this particular elastic rod is comprised of some metal, it is known that alpha f for metal is always positive. E t is also positive, area A is also positive. Therefore, I can quickly predict that isothermal reversible stretching of a metallic wire would lead to an increase in entropy. Similarly, if I go ahead and think about this elastic rod made up of rubber, measurements show that alpha F for rubber is negative, but Et is positive. That immediately tells us that if I am looking at the isothermal reversible stretching of a rubber rod, then there will be a decrease in entropy. Now, we can go ahead and we can estimate other thermodynamic properties like the change in internal energy upon isothermal reversible stretching of the elastic rod. And how can I do that? Obviously, I know that du equal to Tds plus Fdl. Now, I am looking for stretching under isothermal condition. So, I must find out del u del L T. Using this expression, I can write it as T into del S del L T plus F. Very simple application of the rules of partial differential that we have learned in this course. Therefore, I can now express the partial derivative of u with respect to L under isothermal condition in terms of measurable properties like the Young's modulus and the linear expansivity of the rod. And as you see that at a given temperature, you can find out all the quantities on the right hand side, and thereby you can predict the change in internal energy upon isothermal reversible stretching of the elastic rod. So, in summary, what we have learned here is as follows. In the majority of the lectures in this course, I have considered ideal gas which undergoes an increase in entropy under when it is undergoing isothermal reversible expansion. Today, I have shown you two general systems which are very far from ideal gases, because these are interacting systems. These are real systems where the constituent particles interact with each other in a highly non-trivial way. And I find that by using the principles of thermodynamics, I can very easily predict whether under isothermal stretching there will be an increase or decrease in entropy, and I have done so in terms of measurable properties of the elastic rod, which now depends on the material with which the rod is made up. So, as you see that since the linear expansivity of a metal wire is positive, there will be an increase in entropy, and since the same quantity for a rubber wire is negative, there will be a decrease in entropy. So, this particular lecture was planned to show to you what exactly is the scope of thermodynamics. The principles of thermodynamics are general enough. They can be applied to any system, and they can be used to explain experimental data on macroscopic properties of the system. For instance, for the elastic rod, which is a highly non-ideal system, we could actually predict what would happen to entropy as the rod undergoes isothermal reversible expansion. But thermodynamics does not bother about why for the metal wire the entropy would increase and for the rubber rod entropy would decrease. What it does at most is to say that, well, the linear expansivity of the metal wire is positive and the same for rubber rod is negative, and that is the reason why the entropy will increase or decrease. But it will not tell you why at the underlying molecular level this macroscopic property is varying the way you are finding it. That is the domain of either quantum mechanics to deal with the interactions between the constituent particles, or statistical mechanics to connect the microscopic world to the macroscopic properties. But that is much beyond the scope of this course. Therefore, a final reminder of what thermodynamics can do to you. It can give you equilibrium or time independent properties of any given system at the macroscopic level. It does not contain any dynamics, neither does it contain any explanation at the molecular level of why a property would change in a given way or in some other way. Thank you.